Hello, and welcome to another Into the Terminal. Today, we're going to be talking about some Linux performancey things. So, Nate, do you ever have Linux performance problems?
No, never. Everything's perfect. There's
Yeah.
never there's never somebody using up all of your network or disk at some weird and inconvenient time
2 in the
ever.
morning is my favorite.
2 in the morning. Yep.
And the report is almost always the same. It feels slow.
It feels slow.
Yeah. And I'm like, oh, good to know that we're going to be doing actual work based off of your feelings. Excellent.
Yeah. Yeah. Just like it feels bad.
That's right.
Right.
It, I think it feels unimportant.
It feels unimportant. There you go.
But to help with this, because when it feels slow, you have to figure out whether it is or isn't slow, and there's a whole bunch of things that one can do to try and find out what that is. So today we're going to be talking about a couple of instances I've set up where they are definitely borked, and then we'll use some tools to help troubleshoot the borking, and then towards the end, we'll have to see. I don't think we have enough time for 3 borking things. So instead, we'll just talk about some tools that one can use because there's uh, not a ton that you can do about that last thing. Well, anyway, Nate, why don't we jump into the terminal? We can start us off.
Let's do that.
All right, so here's my machine. Feels slow, right? In fact,
Close.
I mean, we can DNF install -y lsof, and man, this is
That,
usually very fast, but
that does feel slow.
it does feel slow. Not today. So let me Control C this, and we can start taking a look at what's happening, right? But when I run other stuff, right, that's not feeling slow, right? Like, well, that's slow. So it's weird that like some stuff is slow and some stuff's not so slow. That's goofy. So Nate, what's the first command that one might look at to see kind of like overall what's going on in the system?
My usual go-to is top.
I like it. That's my go-to as well. So when we look at top, a couple of things. One is you may have gotten something more than it's slow on this machine. You actually might have been paged by your monitoring service because the load average is pretty crazy. Um, Essentially, load average is the number of runnable processes on the system that are in the CPU run queue. And so essentially showing you like a queue depth. And that's not one for one. It's actually run through another bit of math where they use a logarithmic algorithm to kind of smooth out any spikes that one would see in the load average. But essentially, you can think of it as the 1, 5, and 15-minute run queue depth averages, right? How many jobs are queued up in the CPU run queue? So this is going to be interpreted a couple different ways. Um, One thing that you may need to know is how many CPUs do you have?
Mm-hmm.
So if you have CPUs and each one of them has, let's say there's 4 CPUs and each one of them has one job in their run queue, then this load average would be 1, right? Because there's one job in each of the CPU run queues averaged together. So having a CPU load average of 1 is not necessarily a bad thing, right? That you've got one queued up job for every CPU waiting for its turn to do runtime. It's really going to depend kind of on what the CPU is really doing and what the jobs are and whether you're really having problems or not. But in this case, like we were trying to do stuff like install software and it was like really slow. But then when I looked at my local file system, everything was fine until I did a DF and then it was really slow again. And so here we're actually seeing a problem. The other thing that in this top output that is demonstrating a problem is notice under percent CPU for all these different processes, it's about the same.
Mm-hmm.
So the situation that we've got here is that I've got a bunch of jobs and they're being swapped on and off the CPUs. And as a result, they're all getting roughly the same amount of compute time. And so because they're all getting the same amount of compute time, I can see that they're just like taking turns on the CPU all the time. So the CPU is kind of like in this run queue hamster wheel where it's just like running all these jobs in equal amount of time. And that's an indicator that the system is actually very busy with CPU intensive somethings. And that's actually the cause of my slowness, right? So this load average of having all these things queued up in the CPU run queue is actually legitimate. There's a bunch queued up there, and there's so many that each one is only able to consume 3.8% of the CPU clock cycles, right? So if I had fewer of them, maybe they'd consume more CPU time. So that's like the root cause of my problem. Now, what can we do to fix this problem? We could do something like if all these jobs are required, we know that our CPU consumption is kind of like hit a threshold where I'm just not getting enough throughput on it. So I could upgrade the machine. I give it more CPUs, and if I give it more CPUs, then each one of these jobs is able to consume more CPU time. It could be that these are runaway processes and they shouldn't actually be consuming CPUs at all. So maybe I need to look at it and actually like kill some stuff off to run less things. But that's again going to be something that you have to determine for yourself based off of your own machines. So one of the keys to like troubleshooting stuff is knowing what normal looks like. So when it's abnormal, you can one, identify that it's abnormal, and then two, figure out what you should do to fix it. So in this case, I'm going to make my my screen a little bit bigger here so we can actually see maybe what's there. So you see that all these commands are DDs, and I'm just
That's weird. Why would someone do that?
He's probably silly.
Maybe to demonstrate a disk bound problem or something.
So I actually spun up 26 of these, right? DDing IF, the input file was dev0, a never-ending stream of null characters or 0 characters, and the output file was dev null, so I just like threw them away. And essentially what I did by creating this like virtual device to virtual device copy is I'm making the CPU transfer things between the two virtual devices. So it's like taking up all the CPU time. All right. But let me make my window smaller again. Maybe.
Looks good.
All right.
That's even better.
Now that I've let it kind of sit for a moment, and I've killed off all these jobs that were consuming all my CPU time. Now when I run top, notice that the load average is starting to come down. All right. So before it was like 23 or something for the 1 minute load average. And now it's like ticking down as more minutes are coming by and we're doing more averages. And then after a while, that 5 minute run queue average will start ticking down. And after a while, that 15-minute run queue average will start ticking down. And I'll be back to like a normal load average amount. And then when you look at the actual the top output, right, we don't see this pile of identically CPU consuming applications anymore, right? Instead, we see this one that's consuming 1% of the CPU, and then there's another one consuming 0.7%, and there's another one consuming 0.3%. So this is a pretty not very heavily loaded system. But this like variance in how much CPU each job is consuming is a more normal state to see. All right. Cool. I wanted to show a couple other things on this though. So let me make my problem again. There we go. All right. So I just spun up a few to, tweak my load average. One of the weird things I noticed was like when I was doing commands like ls, that was not slow, but when I was doing other stuff like trying to install things, things were slow. And that's actually due to C groups. So one of the things that you might be interested in is how we actually control how much CPU time things get. So we could do something like systemd cgls, right? That's our C group is a resource control technology that's built into systemd. And so here we're just doing a listing of the C groups. All right, so this is kind of like what each of the C group identity, or I should say the list of the services and things that are being controlled by a certain C group are. And so you can see that there's the system slice here. And then later on, the other big category is user slice. And if I scroll down in the system slice, right, there's all of my DDs, all right, using up resources in the system slice. And if I go a little further, oh, that's the end. I don't see the user slice. But the user slice is where we like control resources assigned to user space processes. And that's why some things like ls were working without delay, whereas DNF was not working without delay, because DNF is using system resources, which were the things that were being taxed by this pile of DDs that were being used. And the ls command was part of my like local user environment stuff. And that was going to be covered under the user slice, which has a different set of resource limits. And so we do that to try and keep system tasks and user tasks separate. And then generally there's some rules on how they're managed, which make sure that if you have too many of one, it doesn't affect the other, right? Usually it's the other way around, where like users are doing crazy things and that jacks up system stuff if it consumes too much resources. So we put some rules into place to kind of constrain a little bit. All right.
One more great feature of systemd.
Yes. I mean, it is, everyone says it needs to do init things, but here we're essentially, because it's managing all the services on the machine, it's then making more decisions about how it should manage the services on the machine, which is different from some of the other more traditional init.
Right. C groups is one of those things I think is a pretty cool addition, right, with systemd. The ability to, I mean, each service essentially gets its own little C group, which means you can, they're not always done out of the box, but you can limit a specific service, right? Like you can say you get this much memory, that much CPU, that sort of thing. Pretty cool.
Right. And then the other one that I found that was kind of nice is systemd CG top. Because, you know, who doesn't need more tops?
We need more tops.
Tops are the best.
Additional tops.
Yeah.
And all the top spin.
We're actually going to cover a lot of tops today. But so this shows you the systemd C group top. So you're looking at like which C groups are using the most resources, right? And you can see that the system slice there is using 99% of the C group, the CPU. And then underneath that, this one that's abbreviated and we can't see because my window is too small, is using 98% of it, right? So you could actually go through and like look at what's in that service slice to see what processes are in there that are consuming so much of that CPU. And that might be, if for some reason top isn't showing you this list, this would be an alternate way of getting access to this data that you might be wanting to introspect to figure out what processes are actually your problem. All right. So yeah, that's troubleshooting a CPU bound system, right? The key things are to know that you have a lot of runnable processes, right? Load average is a good proxy for that. And then you can look at like how much individual CPU time they're getting. And it turns out when I was setting up for this example, the more DDs I was running, the smaller amount each one of them was then responsible for getting when I looked at top. So if I spun up like another 20 or another 30, that amount that each one was getting would just be smaller and smaller and smaller. And that tells me that I'm CPU bound, right? That I'm consuming all of it. And when I'm running additional runnable jobs, it's reducing everyone's overall CPU time because I now have more runnable jobs. And that's the key that you're looking for to figure out that you're a CPU bound performance problem. So Nate, we have a new sponsor this week.
We've got a new sponsor. I feel like we're officially getting down the list of sponsors here because well, you'll find out in a moment, right? You've probably heard these ads before. All right. So, in today's unpredictable economy, you should invest in a currency that you can trust. When cryptocurrencies crumble and AI takes a turn, you want a currency that retains its value like nothing else. That's right. Silicon. Not gold, silicon. Specifically, this box of old hardware right here. Because you should invest in my past mistake. Wait, no, that's not what I mean. For a mere $1 million, you can invest in something that holds its value, like this. 1 gigabit network adapter. A whole gigabit of Ethernet right here. You can invest today. Or this ancient Chromebook. I mean, who doesn't want an old Chromebook, right? Think of the uses that you could have with this Chromebook. $1 million. Or this thing that I'm pretty sure is an old host bus adapter, fiber channel. Yeah, you want it. You want this. You want it. You want it. But last but not least, in today's cryptocurrency and AI fueled industry, a GPU. How old is it? I don't know, but it's got a VGA and a DVI port. So you do the math. So $1 million, right? So when everything's getting more expensive, why not invest in something that you know is worthless, right?
Old silicon.
Old silicon. No, it's not. Silicon.
It's
not. Silicon does not age, Scott.
Vintage silicon.
Vintage silicon. There you go. And right. Rick, you might recognize that network adapter. I bought it from you years ago.
All right. So now that we've heard from our sponsor, Silicon Investments Limited LLC. Esquire.
Oh, I didn't say the name. I didn't make up a name. I mean, they didn't. There'll be a link in the description where you can send your $1 million.
So I have successfully broken my machine in yet another way.
Well, good. That's important. That's important. So let's bring up your newly broken machine.
Thank you. It looks just like the old broken machine. How'd that happen?
Identical.
All right. So again, like you're being paged about the uptime.
Whoop,
again.
Whoop, whoop.
Yep. And so if we just look at uptime, right? It's not great. 30 runnable processes indicates a problem. Maybe, probably. But this time when we look at top, I don't really see a bunch of stuff. Certainly not 30 things that are all the same. And if I quit, maybe make my window a little bit bigger. Oh, I could kill off those DDs.
Oh, you didn't kill them off yet, huh? Yeah.
There you go.
You're totally breaking your broken machine. Yeah. It's not broken in the right way.
but now when I look, like I'm not seeing anything like I saw last time with DDs, right? That's like there's not a whole pile of these runnable processes. It's like normal stuff. And yet my load average is a bit stupid.
Yep.
Well, it turns out there's another thing that causes high load averages, and that's disk I/O problems.
Yeah.
Yeah, and we could figure that out real quick by doing disk I/O things like, oh, I'm running DF, and like it's not gonna come back ever
Because it can't get to the disk because disk I/O is all bound up.
That's right. And if I do something like, let me install LSOF, because that's a great way to like figure out what some problems might be. So give it just a second to install. When I try to run LSOF to list the open files on the machine, right, that might help give me some insight as to what the file problem might be. Nope, not going to come back. Never going to come back. So maybe we start to diverge and talk about some other tools that we might use for trying to gather some troubleshooting information. Maybe we try something like VMstat, right? You're like, wait, why would I run virtual memory statistics to troubleshoot an I/O problem? But Nate, right here and here in this section, it tells you about I/O happening on the machine. You can even do a IOstat, run it every 5 seconds for 10 times. Oops. Let's try that again. VMstat.
You're getting ahead of yourself, right?
I am. So here we're seeing our like up here, we're seeing our kind of accumulated total. And then on the runs after that, every 5 seconds, we're seeing the differential between that baseline and current. And you can see that there's zeros. So every 5 seconds, I'm doing 0 disk I/O.
So is that in and out, BI and BO? Is that like bits in or
blocks
bytes in?
Blocks in and blocks out.
Okay.
So now you're like, but Scott, you said this is a disk I/O problem. And yet,
but there's clearly nothing.
Yeah.
Well, that's because there's nothing actually moving, right? That's what you're trying. That's what this is showing us here.
Right. So let me install another tool that we may use. So I ran it by accident. It's not there yet. IOstat. That comes from the sysstat RPM.
You're going to be able to install it with your disk all bound up like that?
Yeah, because I know exactly what the problem of the disk is, and it's not like my hard drive. It's something else. Okay. All right. So now
that's the convenient thing when you've caused the problem, right? You know,
that's right. When you've broken it. So here, IOstat gives you kind of some overall usability things, right? Your CPU consumption, and then it goes through each disk device and gives you some details about what that disk device is doing. And just like VMstat, you can also run it over an interval, right? So I could do IOstat, run every 5 seconds, 10 times, right? So it starts off with that kind of overview summary, and then we'll wait 5 seconds, and here's the incremental, right? And it'll wait for 5 seconds, and then give me the incremental. And so just like before, what I'm seeing is that there's no traffic to and from SDA and SDB. Oh, there's a little bit of traffic. Yep. It seemed to be fine. Yeah, so here we're getting more than what we got under VMstat, right? VMstat, we got blocks in, blocks out, but it was across all devices in aggregate. And here what we're getting is transactions per second. So you're actually looking at how many disk I/O transactions you're doing. Kilobytes read per second, kilobytes written per second. I don't remember what DSCD is. And then there's kilobytes read and written. And I've forgotten what DSCD is. So there's not a whole lot going on to our disk devices here. But yet, I told you it was an I/O problem.
All the signs say it's an I/O problem, but none of the data supports an I/O problem.
Yeah.
Yet.
So there's other kinds of I/O that you could have,
Yep.
So my disk drives or disk devices attached to the machine look fine, but there's other file systems that I can attach that are not disks, but they're treated like disks for tools like LSOF or DF because they're mounted into the file system. But those other disk devices are network attached storage. And that's the problem here, right? It turns out that I've got a NFS mounted file system, and the server side of the NFS mounted file system has gone belly up. And so all these activities I'm trying to do against that NFS mounted file system are stuck. And that's also why they're not using any CPU time, because they're stuck. And so like periodically the CPU schedules it and goes, nope, still waiting on IO, and takes it back off. So one of the things that we could do to try and figure out if this was our problem is all these things that are waiting on IO to resolve have a specific state in their process state for PS. So let me take a look at the man page for PS, and we're going to jump to state codes.
So I have an update from chat. Apparently, DSCD means discarded.
Oh, very cool.
There you go.
Thank you, Rick.
And I would tell you who told me that, but for some reason, YouTube is showing me handles instead of names, so I have no idea who these people are, whether they're regulars or not.
Very good. So when we look at these process state codes that you get in a PS output, for example, that first one, D, uninterruptible sleep, usually IO. Guess what? It's IO. So if I do a PS AUX, right, to give me all processes, to show me the username, not the user ID number, and X says show me all processes, including those without a controlling terminal, like daemons and backgrounded jobs and like other stuff. I'm going to get all the processes on the system. But I'm not interested in all the processes. What I'm interested in all the processes that have a state of D. And I'm also going to use my little trick to also eliminate the grep command from showing up matching itself.
Magic.
So here we go. These are all of the D processes, all the uninterruptible sleep processes. And you can see that all of them have something to do with /MNT. And so if I try to look at /MNT, there's my problem.
Now you're hung.
Right? Yeah.
And you're giving me nightmares, because I remember the days when a network attached storage share, if you tried to access it at all, like the whole system would just
grind to a halt.
Like the whole shell would have to be killed.
Yeah. So now in modern NFS implementations, they all like honor the interrupt signal, right? Which is what Control C is. But yeah, once upon a time, like once you attach to it, like that was it. It was uninterruptible forever, and you could never interrupt it. So yeah, we've made it a little bit nicer. All right. So we can also do things like kill these jobs. Right. So if I kill all LS, bam, there's the 30 LSs I spun up that were like jacking with my uptime, or I should say my load average. And it killed all those interruptible sleep jobs that weren't really consuming CPU because there was nothing for them to do.
Right. They weren't actively doing anything, but they were still queued because they couldn't finish. Right. So they messed up the load average.
Now, this was a very contrived example to use LS. Let's talk about real life. Right. What if this was your website?
Yeah.
And it was retrieving data off of this NFS share. That means that all your web server processes are stuck waiting on that data to be retrieved, which means all your users are getting timeouts because after enough time, like it'll just stop connecting because that IO request is never going to resolve. So IO problems can sometimes have really weird symptoms.
Yeah. And it gets,
and so
it gets even weirder as you move up the stack, right? Like, what if that was your database that was the back
Oh,
end for some other thing, right? The website is slow. Well, why is the website slow? Oh, well, it turns out the database queries are slow. Why are the database queries slow? Oh, well, it's because the database itself is slow because it's this, that, or whatever, right? Maybe it's not that IO is so congested that it can't get a response, but it's all the responses are slow, right? And I mean, I remember spending what felt like an eternity troubleshooting that exact problem where the database was on like an iSCSI volume or a fiber channel volume, and the slowdown was actually on the SAN, not even on
right.
the system that we were on.
Yeah.
So yeah, it's sometimes these things really get difficult to track down, but you just gotta take it a step at a time and identify each thing and try to cut that out of the equation until you find what's actually causing the issue.
Yeah. So uninterruptible sleep, like that's one of the places where you can very quickly identify what process is having IO problems, because uninterruptible sleep is usually an IO problem. But there's
As
other
a
things, right?
as a human with children, uninterruptible sleep sounds awesome.
Indeed, indeed. Take a lesson from your small furry friends that you have there in the house, Nate. So some other things that could be IO problems. Networking can be an IO problem, right? And it has a lot of the similar hallmarks to the disk IO problem I just showed you,
Yeah.
where it'll have like weird things are causing it, but how can you identify it, right? So one of the things you could do is you could take a look at LSINTR. Whoops, let's try that again. LSRQ. So these are your interrupt requests. So every device on your machine is assigned an interrupt request by the kernel. And you can see that one on the top that has the most interrupts, that is the local timer. So how we change things on the CPU run queues and on and off the CPUs is we send an interrupt and we say, hey, it's time to swap these things out. So
Hey,
the
do a
longer your
thing.
machine,
Yeah.
yeah. So the longer your machine is up, the bigger that number is going to be.
Right.
Right. And it's normal for it to be a stupidly large number. But then we start to look at some of these others, like this PCI MSIX, and then it's got like this weird PCI ID. That looks kind of, I don't know.
VirtIO0 makes me think that might be for disk.
Disk. Yeah. And then as we like scan through this list, I don't see any network adapters. And it turns out that's because this virtual machine is actually sharing multiple devices on the same interrupt request. So those top ones that we set our VirtIO0 request and VirtIO1 input, those are disk devices attached to that interrupt request. But that PCI MSIX blah, 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 that's probably our network adapter. All right, so sometimes it'll actually say like ETH whatever. That's cool. That's great because then it's really easy to identify. Other times, like cloud instances, maybe it doesn't have such a great name. But what you can look at is how big that number is. And just like we saw before with like VMstat and IOstat, if I take a look at it after a little bit, so was it 30,965? Right now it's 30,991.
I just ran this on my home lab machine, and you're right. The devices, the PCI, MSIX, yada yada yadas. At the end of those lines, instead of that VirtIO dash whatever, I've got the Ethernet adapter names. I've got the disk names, the NVMe disk names. Ethernet adapter is probably there's NVIDIA there for the GPU that I've got in the thing. So yeah, it looks like it's however the kernel knows your device is what shows up at the end of that line.
Yeah. So we can see that over time, like when I checked the interrupt signals again, it went up, right? Because there's system activity happening. But the thing to look for network problems, like if you're having a ton of network traffic, well, every time network traffic is received by your controller and it needs to be processed by the kernel and ingested into your system, it raises an interrupt to say, hey, come get this data. And so if you suspect that it's a networking, that like there's too much volume for networking, this is a real quick way that you can check to see, how many interrupts am I getting? Am I being told constantly that there's a lot of data to be had? And so you can look at how often the interrupts are being signaled and look at the differential between running the ls-irq command to see kind of the volume that's being pushed through in terms of number of interrupts. And number of interrupts could be used for kind of a proxy for amount of data coming in or off of that device. So that might be a way that you can, like, if it's not a IO problem with your network IO, but it's actually like a network throughput problem where we're like maxing our interfaces, we could maybe see that through things like very high interrupt request rates. All right, another one, and we have to install this one off of Apple. And I'll install actually two, IOTop, no, IFTop, and HTop. So I said we're going to do all the tops today.
All the tops.
Right? All the tops. So IFTop is your interface top. So looking at the interrupt requests, that's a very quick and dirty way of looking at kind of traffic flows between different devices on your system. IFTop is giving you the interfaces and the data that's being transacted through them, and then it's updating it periodically so that you can actually get a better real-time picture of what traffic is coming in and out of your box. And then down at the bottom, it's giving you your transmitted and received totals, so you can actually see whether it's like you sending a bunch of stuff, you receiving a bunch of stuff, or some combine of the two. All right. So this one's pretty handy. And it is from the extra packages for Enterprise Linux repository. So this doesn't come with RHEL natively. You need to install it from extra packages for Enterprise Linux.
I like this because there used to be a tool I depended on called NetTop, and that went away. And I didn't know what replaced it. So IFTop. Conan Kudo was suggesting a tool called Below, which I've never seen. He says it's also in Apple. I have never seen that yet.
I will check it out later. The other one that I see people advertising all the time is HTOP. So colorful. HTOP, it is colorful. It also has, if you look down at the bottom there's the function keys. So you can do things like sort by a certain thing. By default, it's sorted by CPU usage. But you can also change the nice value on stuff using this tool. You can also use the nice command. But if you are unfamiliar with nice, so that pri field, the priority field, that is a priority number that runs between plus 20, the least important priority, and minus 20, the most important priority. And you can see a couple in the middle there actually have a -4 assigned to them. That's their nice value. And right. So by making adjustments to the priority, you can make it more important to the CPU and have it like preempt other jobs when we're doing multitasking on the CPU. So if all the jobs are priority 20, then they all take turns going on the CPU. But if those two jobs that are priority 16 ask for CPU time, they actually get to preempt all the priority 20 things and take the CPU time that they want. And the only way
we used to, in our old hypervisor cluster, which was like back in the days before we had actual like graphical environments to manage the things. This was a libvirt with cluster suite managing its resources. We used to make disks using DD, right? And of course, as you've shown earlier, DD can actually put a load on both the disk and the CPU. So we used to use NICE whenever we made a new disk. We'd use NICE to make sure that the DD process didn't preempt like a virtual machine, right? So that's, a practical use case for where that might come in handy.
Yeah, and it turns out that by default, if you're using a graphical desktop, because server with GUI guy over here, the locally running user things actually get a slightly improved nice value. So that when you're doing things like you click on your web browser window, or you click on your terminal window, the graphical user interface gets a better priority so that it maintains this like responsiveness to the user, as opposed to what we saw earlier when all the things were the same priority, like they all had to share CPU and that made things feel slow. So we actually give a priority bump to the locally running user processes so they don't feel slow, even when the system is busy.
Especially if that's the way you're administering the machine, right? I mean, you can't have the entire GUI running sluggish while you're trying to get to a terminal to do something, right? So
right.
It's got more than just a user experience. It's also got a practical benefit there.
Well, and I think I've said before on other shows that Linux people are smart people, and the developers that manage Linux and write the kernel and do a bunch of other stuff are not dumb. And so they'll do things like, oh, people don't like it when their desktop is sluggish because they're running some IO or something in the background. Cool. We'll just automatically adjust the nice value, and then they won't have that problem anymore. And so the IO is still getting done, but the user interface and like someone's interaction with the machine is not encumbered with that additional stuff that's happening, right? So these are just like normal things that happen on your Linux box.
Things you never even knew were there.
Exactly, because it just works.
Just works.
So the other thing is like instead of the CPU and memory and swap and all the CPU states and all that stuff, that's kind of translated into a little text-based graph for you, so you can kind of see like, is it good or bad, or how are things going? And we can see that, swap 0, cool. CPU very low, memory mid. So there you go. Cool. So those are some things that you might also look at, and then we're starting to get up in time. So this is where I thought we were going to run out. The other thing that we were going to talk about today is memory usage. But memory usage is normal. Where you run into problems is when the killer gets started up, right? That's the out of memory killer. So when you exceed the amount of memory that you have, this kernel thread starts up and just starts like almost randomly killing processes. And there will be messages about that in both the journal log and var log messages to let you know the killer has started and it like killed off some processes. So if you see killer messages, that tells me that you're having memory pressure. But killer is not the brightest. So essentially what it's going to do is it's going to kill processes, thereby releasing their memory to then fix your out of memory problem.
Right.
The
problem is the thing that's using all the memory is probably the important thing on the machine.
but it'll kill like other stuff. Like it might kill your SSHD daemon, or it might kill your NFS server daemons, which then like mess up all of your clients. Like we saw earlier with my O problem.
We had a Gluster storage array, and the killer would sometimes kill off the Gluster client on the machines that were clients to Gluster. And it was like, oh, good. The thing that provides all the storage to the application, that's what you decided to kill.
Well, so I said it's seemingly random, but it actually has some rules.
Yeah.
And so in /proc, which is giving you a window into the running kernel's memory, you'll see all these numeric directories. Right? Those correspond to the process IDs of the processes running on the system. And so let me do a pid of SSHD. All right, so SSHD is running under process ID 2044. So if I go into the 2044 directory, these are all the things about the SSHD daemon. And one of the things that's in here...
score.
Yeah, score. So the out-of-memory killer will look for things that have a low score, because they're not important, and we should kill them off if we are running into real bad problems. But if you actually kill off SSHD, how do you SSH into the box to fix it when it's having problems? So one of the things you could do is put a value like 10. into adjust. And that will like adjust your score. So now it's really high, which means if is looking for a process to kill, it's going to kill off things that are lower than score 1059 before it kills SSHD. And so if there's important things that you want to make sure don't get killed by out of memory killer, you can adjust the score, but this is dynamic.
That's
so
in memory.
You may have like so you may have to do like a startup script where you adjust these things when you start the machine. Because if I shut down the machine, this adjustment gets lost. And then when it starts back up again, it'll have the default score again.
And that was what we ended up doing with our Gluster problem. We figured out what process the Gluster client was, and we made it adjust the score at boot time.
Yep. And that's a great
we still had the out of memory problem, which was actually a memory leak somewhere that had to be fixed. But at least in the meantime, it wasn't killing off our storage.
Yeah. So that's like one of the ways that you can try and control and shape your out of memory experience. But some other tools that will help you get information on memory. We can take a look at free. That's a really easy one. Shows you your total memory, how much is used, how much is free, and then shared and buffer caches memory. This command has changed its output over the years. So it used to be that the free field did not include buffer and cache memory and shared memory. Now it does include those things because those things can be they can be deallocated to go back into system memory and be used for other processes. So more recent versions of free, the actual free amount of memory is inclusive of the shared and buffer and cache memory. But on older systems, that may not be the case. You might look at free and it looks like really small. And then you look to the right and you see the buffers and caches like really huge. That's also potentially free memory. You also get your swap usage out of this. And then earlier I showed you VMstat. Oops, if I spell it right. So VMstat gives you your memory statistics up front. So like stupid line wrapping.
So many columns
right there. So this gives you your free memory, your buffer and cache memory, your swapped memory. That's what the 0 is there at the first one. And then SISO, that's your swap in and swap out. So here, if you're thinking that you're having a paging problem and that's what's causing you your memory problems, you can actually run this on your interval and you can actually start seeing whether there's swap in and swap out activity. And that'll tell you that that is happening. And then the other one that might be interesting is also in proc. Proc amendment, though, this gives you a lot more detailed information about how memory is being used. So you get things like the total and free and available and how much is being used for swap and cache, buffers and cache and swapped. Guess what? The free command and VMstat actually get their stuff directly from this file. But then you also get things like inactive memory and anonymous memory. Anonymous memory is stuff that is tied to a specific process and it's not eligible to be swapped. You get things like file caches. So you get more information. And if you keep going, you get things about shared memory. And then down at the bottom, you get things like huge pages, which the other tools don't show you, as well as how your direct mapped memory looks. So this is like way more detail into how the system is utilizing memory and what it's set up to do for its memory. All right, so that's like your troubleshooting tools for memory problems. But how you usually experience memory problems is killer starts up and starts killing off seemingly random things, and that's causing you your issues. So you can look in the logs and see what that is actually happening and then what it's also killing off. And then you can start using these memory tools to try and figure out like who's using all the memory, what the actual state of memory on the system is, things like that. All
So there
right.
was a quick question in chat when you started talking about swap, and I think we've heard this before, but with modern systems, I'm going to paraphrase a little bit here. With modern systems where, memory used to be very expensive, right? So we would put just enough memory in, and then we would depend on swap, and then you'd have an algorithm you'd use to decide how much swap do I need versus how much memory. Well, now it's a lot more common to just throw a whole bunch of memory into a system, and because it's cheaper than it used to be, right? So in a modern system where you may have a lot more memory available, like actual memory, is it still so important to allocate whatever the old algorithm used to be, which was like half of memory to swap? Or does that change now that we have larger memory footprints and larger memory, more memory available generally?
Yeah. So the older like 2x RAM should be swapped. Like that stuff is gone.
Right.
Um, Now there are things that swap is used for. So there are people that want to do like 1x RAM as swap. So they can capture whatever the state of their memory is in swap. Things like when you hibernate a laptop, right? It'll actually
Right.
and not suspend, right? Which basically still keeps power to the memory modules, but hibernate.
Right.
Hibernate means it stops using power entirely. And what it'll do as part of that hibernation process, actually write all the RAM out to the swap space. So if there's not enough swap space, then you can't actually use that on your machines, on your laptops, for example. So there are some stuff that you still need swap for, but I think they're more niche than they used to be. There are
Right.
times like for a long time I didn't run any swap. Like I don't know, the last 10 years or so, I just stopped. Um, and I was fine. But
Yeah.
there's other stuff like how is it used for stuff like K dumps, and there's like random bits and pieces that will use swap still that it's useful to have around. Now we're actually doing a lot more active paging of inactive memory to swap space. So that was a like midstream change on RHEL 9, where the kernel started to change how it uses swap space. If you have swap space, you'll probably notice that it's in use, even if your system isn't overly loaded with activity and stuff. And that's now the new normal for the Linux kernel. So if you have swap space, it's probably being used because we're more aggressive about swapping out inactive pages. Um, and so, like, if you didn't have swap space, then you wouldn't be able to aggressively swap out inactive pages and have more memory for your active stuff. So yeah, it's kind of a mixed bag.
Cool. So we're
And
almost
then
out of time. The only
you
thing I was
wanted to
going to
show something.
show, yep, the only thing I was going to show was I don't exactly have a demo for this, but I wanted to make people kind of aware of it if you're not already, and that is the Performance Copilot integration into Web Console. So what I'm sharing here is the Web Console on my machine down in the basement in my home lab, where you too, for $1 million, can still buy subterranean colocation. But anyway, on the overview page here, if you have Performance Copilot installed, which if you just install the package PCP0conf, PCP-0conf, and there's a plugin for Cockpit, which is Cockpit-PCP. You install those two things, it pretty much automatically starts collecting data and piping it into a place where where Cockpit can read it, where Web Console can read it. So if we just go to this view metrics history here inside of the overview page, and this is zoomed in a little bit, so it looks a little better when you zoom out, but I want you guys to be able to actually see it on stream. You can see it gives me some overall statistics about things that are using memory and things that are using CPU. And this is all in the base web console. This is like how much disk space and IO is going on, and my network interfaces. It'll give me an overview of how many uh, kilobits or gigabits or megabits per second are going through my network interfaces. But if we scroll down underneath here is where the data gets kind of interesting when you have Performance Copilot installed and enabled. And that's these little graphs here. So let me just kick up a little bit of DD going on my machine here. Somewhere in my history. There it is. So I have an iSCSI volume on this machine that I just kicked off a DD to. So what we should start to see pretty quickly is some network traffic That'll be in this column over here, although I see that my headings are missing. Let me just, oh, that was the wrong window. I'm going to zoom back out to get my headings back. So sorry, you'll just have to deal with the smaller text. There, now we can see network usage. So you should see in this column here, we're going to start to see network traffic come up. And it happens, pretty, I don't want to say instantly, but once it starts to track that data, it's gonna start to show up in this graph. The other cool thing is earlier when I was testing this, I caused a couple of spikes, right? And you can see here in the history, it says there's 6 spikes in this particular block. Every hour, it gives you this little summary. You can see here at 10 o'clock it did it, at 11 o'clock it did it, at 12 o'clock it did it. And you can see there, those are the spikes that it's talking about within that block of time. So at 9:48 around or 9:42, there was a spike here in disk IO, right? And here you can see just barely at the top here, if you can see that on stream, the network and disk IO both jumped when I started this DD. So this isn't like, I don't know if I would call this monitoring data that I would trust to go back and try to identify something that happened a half a month ago. But if you want a good overview of what's going on in your system right now in a graphical thing that you can just hand off to pretty much anybody on your team, right, that has access to the machine, this is a great way to get that done. A great way to just kind of get an overview. It's almost like having top or maybe more than top at your disposal right there inside of a nice GUI. So it's a nice tool. Wanted to make sure people were aware of it. That's all.
Yeah, and there's a couple other like small things that I would point out. One is when you have spikes like that, oftentimes there will be links to logs. So you can actually look at log entries that happened during that time when the spike occurred. So it'll automatically capture those timestamps and make them available to you in the tool.
Right.
And then Nate, you said, I don't know if I trust it or not. It turns out the Performance Copilot collected data that is driving this thing is what all the other monitoring utilities are using. So we're great
Sure.
at collecting all that data, and but what we don't do is alert based off that data, and then have things like thresholds to make decisions off that data, and that's what
I would
Nagios, Zabbix, like all those guys are doing.
I would trust it for up to the minute stuff, right? But if you're looking at something like, oh, what happened 2 weeks ago, that data may not persist. I'm sure that's configurable, but you will want to collect that data and put it somewhere for analysis later. When I said you don't want to trust that, I didn't mean that the data is bad. I meant that you may not be able to trust that it's going to be here forever, right? Because it does rotate out. That's what I meant.
Okay.
So anyway, but you're right. If you click on one of these things, right, it'll give me some log data around what occurred around the time of that particular spike, which may or may not be related, right? it says load and network IO, and the logs here are for one of my Podman containers. That's just things that happen in the logs around the time. But you can also look at like I can tell you these are Podman containers, right? It says pod, whatever. But these are things that have large memory footprints, and I can click on it and it'll take me to the related thing in Cockpit. Like this took me to the Podman containers management plugin for Cockpit, and it's showing me that particular pod, right? So now I can try to troubleshoot, why is this thing taking up so much space? Well, that's because it's a game server and it takes up a lot of space, but you get my point.
Yeah, they've done like tremendous work on Cockpit over the last, I don't know, 6 or so years, since it was originally included with RHEL 8. So
Right.
Cockpit is primarily engineered by Red Hat engineers, and the virtual machine management in it is great. The Podman container management in it is good. They added this performance management part of it, which is cool. They're doing a lot of stuff with
The
Cockpit.
virtual
That's
machine
really
management is what I use it for mostly. That's the reason it's on this machine, and it is slick. It works really well.
So, cool. Well, I think that runs us off our prepared remarks today.
That it does.
Who
knew an hour about performance troubleshooting? It's almost like there's a lot to talk about.
Exactly. So next week we'll be doing another into the terminal. We haven't selected our thing yet. Nate, we need to get better about like picking an arc or something, so we can get a little bit more lead time than
But
1 week every week.
Remember, everybody, invest in silicon.
That's right.
Old
Oh, and don't
silicon.
forget to like and subscribe. Invest in us. Like and subscribe. But yeah, so until next week, we'll do another Into the Terminal. Thanks, everybody.
About something. We'll see you then.